Welcome to the video presentation Lateral Air Navigation Seminar Avionic Devices. We will provide you with an overview of general navigation principles, navigation systems which implement those principles, and the charts and procedures currently in use. General navigation principles. Any navigational information is useless without a proper reference. Such a reference for direction finding is the north reference, but north is ambiguous. For any position on our planet, true north is the direction to the North Pole. Since the magnetic North Pole and the geographic North Pole do not coincide with each other, the direction magnetic north obviously has to differ from true north. In addition, a number of influences on the magnetic field of the Earth, such as geological formations, cause the difference between true north and magnetic north to be variable, depending on your location. This difference is called variation. Ideally, a magnetic compass would point to magnetic north. Real compasses, however, are prone to electromagnetic disturbances themselves. In an airplane, those disturbances can be caused by parts of the airframe and especially equipment interfering with the magnetic field. The difference between magnetic north and the north direction that is indicated by the actual compass is called deviation. Heading is effectively the azimuth angle from the north reference in use to the longitudinal axis of the aircraft. Referencing true north, it would be the true heading. Correspondingly, there is magnetic heading and compass heading. Heading and course are not necessarily the same. Since the aircraft might be flying wind correction angle, which is mostly the case, the heading and course differ by this wind correction angle. Therefore, when a flight is planned, a heading has to be calculated for a certain desired course at a particular assumed wind situation, which can be derived from special aviation weather observation and forecast or other information sources. The TAS, or true airspeed, is the speed vector of the aircraft relative to the air, whereas ground speed is the speed vector relative to the ground. The difference vector between those two is the wind vector. This is the case in a pre-flight planning stage. In the post-flight scenario, the path flown over ground is called the true track, and the angle between the true airspeed and the actual flown true track is the drift angle. It equals the wind correction angle if the wind was assumed correctly. Otherwise, the difference between wind correction angle and drift angle is the drift additional. In the old aviation days, when navigation computers in aircraft were not as sophisticated as they are today, pilots were doing these calculations manually. This is an example of the use of an analog computing tool for pilots that is still part of pilot training today. From a given true heading, airspeed and wind, we will predict the actual ground speed and resulting true track over ground. First, we set our heading on the top index and the underlying speed graph in a way that the given airspeed is just below the center metal ring. Then, we set the wind pointer on the given direction. Now, by looking at the spot marked by the number that is equal to the wind speed on the wind pointer, we can read the speed on the underlying speed graph. This speed is equal to the ground speed. These numbers on the graph indicate degrees of drift either for drift angle or wind correction angle. In our case, the drift angle is 10 degrees to the right. Therefore, to get the true track, we need to add 10 degrees to our true heading. This means that our actual true track will be 280. Navigation systems. In order to navigate from one position to another, one must be able to determine the current navigational information in flight, such as position, heading and speed. The knowledge of those values allows for precise adjustments of controls by either the pilot or the system responsible for control. A very basic and well-known system is the magnetic compass, also known as the whiskey compass. That is, despite all the other sophisticated and highly redundant navigational systems on board, part of the standard equipment of all civil transport aircraft. The working principle is pretty simple. The ferromagnetic needle aligns itself with the horizontal component of the magnetic field of the Earth, and thus allows for determining the aircraft's orientation in relation to local magnetic north. Together with a chart that displays the variation in the area that the aircraft is in, it is possible to deduce the true north direction. As we mentioned before, the compass succumbs to electromagnetic interferences of the aircraft itself. Therefore, the compass does not indicate magnetic north directly. Since the interferences are assumed to be approximately constant, the deviation is measured by technical staff on a regular basis and presented to the pilots in the form of a deviation table that is placed right next to the compass. The table is very intuitive and advises the pilot in a steer this to fly that manner. As one might suspect, by today's standards a simple magnetic compass is not very precise, since it is subject to multiple errors. The whiskey compass itself is suspended in a bowl that is filled with a damping liquid to allow for free movement without excessive swing or wobble caused by the vibration of the panel in flight. In order to be as precise as possible, the construction is suspended well above its center of gravity, almost like a swing. If it were suspended fully free in the center of gravity, the needle would align itself with a total magnetic field component that, for example in Europe, would lead to the needle pointing towards the Earth in an approximately 60-degree angle. The compass would not be readable. This construction and the dip of the magnetic field lines, however, leads to an error that has to be taken into account. When flying a turn, the compass is tilted also, and sensing part of the vertical component of the magnetic field. This influence distorts the reading. When flying turns, pilots have to be aware of this effect when watching the indication and waiting for the moment to roll out of the turn. Acceleration and deceleration also cause the dip of the field lines to manifest themselves in an erroneous reading. Because of the swing-like construction, the compass swings back or forth when the aircraft is accelerating or decelerating. The resulting dip causes, much like in turns, a false indication. For the next compass error, you may now imagine a nice cup of tea with a spoon in it. As you start stirring your tea, at first you feel resistance from the resting liquid in the cup, much like the needle that has to move through the liquid in the compass bowl. As you continue stirring, the liquid starts to move along, and at that point, when you let go of the spoon, the tea is still rotating in the cup, and may even drag the spoon along a little. This kind of vortex also forms in the whiskey compass in prolonged turns. The error resulting from that indication overshoot after rolling out from the turn is called the spin error. As you might have noticed, a magnetic compass seems not to be the ideal instrument to rely on while changing the aircraft's heading. In this situation, the directional gyro is a better alternative. In the cockpit, the pilot sees a heading rose that he can freely calibrate with a knob to set the current heading. Usually he would do that in straight and level flight, where the magnetic compass is most reliable. When the aircraft makes turns, the indication will show the changes to the heading precisely and without the flaws of the simple magnetic compass. This advantage is gained by using a gyroscope that is mechanically tied to the heading indicator and sensitive to movements around the vertical axis of the aircraft. For short-term use, the directional gyro is more precise than the compass, but it is influenced by gyro drift. This causes the indication to run away as time progresses, making it necessary to update the current heading manually, for example by looking at the magnetic compass at an appropriate time. The drift of the gyro is caused by several factors, such as the rotation of the Earth. To understand this effect, imagine yourself standing on the North Pole holding the gyroscope. If you would not update your instrument, you would have apparently changed your heading by 180 degrees when the Earth has turned 180 degrees after 12 hours, although you never actually turned. This effect reduces with the sine factor of latitude when you move away from the poles towards the equator. A smart combination of the advantageous properties of magnetic field sensing and using a gyroscope is the use of a remote indicating compass. This indicator combines the directional gyro with a flux valve that is usually built into a part of the airframe that is as far away from the electrical equipment of the cockpit as possible, for example in the wing tip. The flux valve is essentially a compass that senses the magnetic field by exciting 3 coils using alternating current and measuring the resulting magnetic field. If there were no other field present, the resulting field would be cancelled out to 0, since the alternating current consistently causes alternating fields for very short periods of time. The interference from the Earth's magnetic field, however, causes a measurable difference in the resulting field, making it possible to deduce the actual horizontal component of the magnetic field of the Earth. But since the flux valve is tied to the horizontal plane of the aircraft, the errors of the magnetic compass are equally prominent when using a flux valve, even though it can produce more exact measurements. This is where the directional gyro comes in. The indicator is wired to both gyroscope and flux valve, in a way that short-term changes are directly influencing the indication without delay. To counteract any drift of the indication, the flux valve is constantly calibrating the indicator as well. However, to prevent the indication of dip and acceleration errors, the flux valve's influence is limited by a low-pass filter, so that changes are not apparent immediately. Thus, the heading indicator does not have to be adjusted manually, while the gyro is slaved by the flux valve. We have now seen some ways to find out in which direction we are looking in flight. This is not enough. We also need to know where we are. The first thing that comes to mind is GPS. It seems to work pretty well, as you can see for yourself using your very own smartphone or GPS receiver in your car. For aviation purposes, however, the system is not reliable enough to be used as a single means of navigation. Let us look at the more traditional and proven systems that allow aeroplanes to identify their current location. One of the oldest systems is the non-directional beacon, or NDB. Basically, it is a station that transmits its identification on the middle and low frequency bands. The idea behind it was to equip aeroplanes with a receiver that could display the direction to an NDB station that the pilot selected using a chart. This way, the flight could be conducted using a route that consisted of individual legs from one NDB to the next, and so on. Of course, over time, these airways that were defined by chains of NDBs became impractical, with more and more air traffic claiming that limited space. But NDBs also allow to identify your position through triangulation. If you read the bearings to multiple NDBs, provided you have reception, you can draw the bearings on a map, and the point where those lines meet should be your approximate position. A job that used to be done by the flight navigator, also an extinct species that became victim to the ruthless progress of computer science in aerospace. Let's take a look at the onboard receiver for NDB signals. The airborne equipment is referred to as Automatic Direction Finder, or ADF. The system consists of 2 antennas called loop and sense that receive the magnetic and the electric component of the signal. This architecture allows, by means of overlapping the individual reception patterns, to create a total reception pattern in the shape of a cardioid, as you can see here. The dent in the pattern is the point of minimum reception strength and gives the best margins to identify the direction from which the NDB signal is coming from. Even the oldest ADF receivers were able to get a fix on the station with an error of less than 3 degrees this way. But there is a reason that NDBs are becoming more and more a thing of the past, as the newest generation of civil aircraft do not even get equipped with ADF. The system is not exactly fail-safe. The frequencies in use are very susceptible to all kinds of disturbances that influence the path of the radiomagnetic waves. For one, there is the mountain effect that leads to false indications by reflection of the signal from terrain. Refraction happens when the wave is propagating towards or away from the shore in an angle between 0 and 90 degrees. Crossing over from or to the water, the radio wave is refracted and thus changes its direction. Another great influence on the ADF is caused by thunderstorms that occur in the vicinity of the aircraft. The interference from the static charge leads to an unreliable indication. A dip error that is equivalent to the correspondent error of the magnetic compass is also an issue of the ADF. The closer the aircraft is to the station, the greater is the angle at which the NDB signal is received in relation to the aircraft's horizontal plane. This angle causes the same problem for the ADF as the magnetic dip for the magnetic compass when the aircraft is banked. Part of the vertical component of the signal is sensed and distorts the indication. In addition, the airframe itself influences the radio signals. This is called a quadrantal error. And finally, the night and twilight effect may lead to false positive reception of stations that normally would be out of range. The effect is caused by inadvertent range increase of the signal through special atmospheric conditions that occur in twilight. Our next system is also ground-based, but you might say it is the next step. The Very High Frequency Omnidirectional Range, VOR. The idea behind the system is that the receiving unit should be able to determine its magnetic bearing from the station on the basis of the signal alone. This is realized by using a two-phased signal from which the information can be derived, the reference phase and the variable phase. Although technically not entirely correct, this image gives you an idea of how the bearing information is created. Imagine the reference signal as a periodical omnidirectional beep and the variable signal as a rotating highly directional signal. If you know exactly how fast the reference signal is rotating, you can deduce the direction from the station that you are currently on just from the time interval that is between your reception of the reference and the variable signal. In practice, the VOR station sends the omnidirectional reference phase and the variable phase that is dependent on the direction. The onboard receiver then determines the phase shift in order to deduce the magnetic bearing from the station. That is also called the radial. This is, however, in general the same principle as you can see in this illustration. The VOR receiver allows multiple instruments to display the radial information. The basic RMI, or radiomagnetic indicator, that points towards the magnetic bearing to the station, the CDI, course deviation indicator, that is designed to follow a specific bearing to or from the station, and the HSI, horizontal situation indicator, which is kind of a CDI but with a movable compass beneath the indicator that is fixed on it. To better understand how these instruments work, we will show you how an example situation is handled using this equipment. This is a VOR, and these are the corresponding radials that it signals out. This is our airplane. As we can see, we are currently on the 070 radial. That means that our bearing from the station is 70 degrees magnetic. Radials are always referencing magnetic north. This is an RMI. It is part of a compass system and shows our current heading, which in our case is spot on north. The thick green arrow is the second navigation system, which is currently offline. In this case, the needles always point to the right wingtip. Our VOR receiver is tied to the yellow pointer. As you can see, the bottom of the needle points to 070, the radial, and thus the pointer is showing the magnetic bearing to the VOR station, the opposite bearing, in our case 250. Say we turn towards the station. This is what the indicator will have turned to. Obviously the bearing remains the same, it's just the heading that changes. Now let's take a look at the CDI. You could say the CDI expects input from you. To be more specific, the instrument wants to know on what course you want to fly over the station at. Take a look at the top of the rows you see on this CDI. Apparently we want to overfly the station at the course of 270, like this green arrow. So what does the CDI tell us? For one, based on the radial we are currently on, the to from indication on the right side of the inner part of the CDI shows us whether we are already crossed the station or still have to fly towards it. Secondly, the white diagonal strip is the deviation bar. This is the indicator that tells us how far off we are in degrees. Every dot of the horizontal dots stands for 2 degrees. If it is more than 10 degrees, it is in full scale deflection, like it is currently in our example. We want to fly on the 090 radial towards the station, so we are on the 270 course when we cross the station. Therefore, our deflection is 20 degrees. We are too far to the right according to the CDI. So, we turn towards our desired course in order to intercept it. As we approach the desired radial, the deviation bar starts to crawl back to the center. In this picture we are already on the 085 radial, meaning that we are only 5 degrees off course. As soon as we are on the desired radial, the deviation bar is straight in the middle. Note how the heading of the aircraft is absolutely irrelevant for this indicator. If we were to turn around now and fly into the opposite direction, the indication would not change. As we approach the station, we enter the cone of silence, the part where no reliable reception is possible. As soon as this is the case, the nav flag shows on the instrument, showing that no interpretable signal is present. When we have reception, the indicator shows our deviation from the desired path again, which in our case is still 0. The difference to the previous indication is the from arrow that is now showing as opposed to the to arrow that was illuminated before we crossed the VOR. Let us take a look how this maneuver would be done with an HSI. The HSI is basically a CDI glued on a heading indicator. The yellow arrow represents the course that we wish to fly over the station at. The deviation bar is the displaced part of that yellow arrow. As we approach the desired course, the deviation bar closens to the center, just like the one from the CDI. This is what it looks like when established on course, on the to side of the station. And that is the HSI after crossing the VOR. So far, we still do not know our position. The VOR allows us to determine relative directions only, at least as long as we do not use triangulation. The other very common way to get a fix on your location is to use a VOR in conjunction with DME, distance measuring equipment. This is how it works. The airborne equipment broadcasts randomly spaced pulse pairs on the UHF band. When the ground station receives the pulse pairs, it responds on a specifically shifted frequency with the exact same pulse pattern. This happens omnidirectional, since this navigational system is about distances only. When the DME equipment in the plane gets a hold on the response pulse pattern from the ground station that resembles the one the plane sent out a short time earlier, the difference in timing from airplane interrogation to the reception of the response is used as a basis to calculate the distance of the airplane to the station. This means that there is no specific identification of the airplane involved. The airplane simply listens for an echo that resembles its cause. This method allows for a total of about 100 airplanes to be using one DME station at a time. Since the DME is usually used together with a VOR, the DME is not tuned separately. The pilot sets the VHF frequency of the VOR station by referencing the chart. The UHF frequency of the corresponding DME is set automatically, since they are always installed with the same defined offset. Interestingly, when there is no actual VOR at a working DME ground station, to be able to receive the DME anyway, the pilot has to set a VOR frequency of a phantom station, so that the DME receiver tunes to the corresponding frequency of the existing DME station automatically. This is how a basic DME receiver looks like. As you see, there is no way to set a DME frequency, only a rotary switch that allows the pilot to set the referencing navigation system, 1 or 2. Also, in case you want to change the VOR station, but at the same time keep the DME station that is currently received, it is possible to use the hold setting that is in between N1 and N2. The display shows the range to the station in nautical miles, the relative speed to the station, and, based on the data, the projected time to the station, as long as the airplane approaches the station, of course. A very important thing to be aware of when using DME is the difference between ground distance and slant range. The indication that you see in the cockpit is the direct distance from the airplane to the station, hence the slant range. This is not the distance you would measure using a chart from the station to your position. The difference between those two increases as your distance to the station decreases. As you are directly overhead the station, the indicator will still display your height over the station and not 0, which would be the ground distance to it. NDB, VOR and DME are, amongst others, not self-contained navigation systems. That means that they require a ground station to be able to generate useful data. The receiving antennas for those systems can be seen here in this example. This is a Citation business jet that is used as a training aircraft. The DME antenna is located right here below the cockpit. The nav receivers that are used for VOR and ILS reception are located just below the horizontal stabilizer of the tail. The ADF sense and loop antennas are on top of the fuselage, just behind the cockpit. Furthermore, you can see the location of the VHF COM antennas on the upper and lower side of the fuselage that are used for voice communication, the emergency locator transmitter, GPS and other vital systems that require a radio transmitting and/or receiving capability. For our last navigational system, let's take a brief look at a self-contained one, the Inertial Reference System. The IRS is a highly precise instrument that works by means of measuring angular and linear accelerations in all spatial axes. Since it does not, in principle, receive any external information, it is prone to the same drift problem as the gyro of a classic heading indicator that has to be reset after some time to avoid an indication runaway. But in comparison to a simple gyro that requires a correction every 10 to 15 minutes, the error behavior of the IRS is definitely better. For the horizontal position, the system is within an error radius of 650 meters after a whole hour of flight without any external information update. This is still better than the worst case accuracy of a VOR DME station that is considered to be approximately 900 meters. Before flight, the system has to be aligned. In this phase, where the airplane shall be as still as possible, the system detects true north on the basis of the measured centrifugal acceleration that is caused by the rotation of the Earth. Also, the current attitude of the aircraft is detected through the accelerometers of the system. Later in flight, the indication of heading and attitude is based on integration of the angular acceleration of the system's gyros. In conjunction with its accelerometers, so is the lateral position. The flight management system, amongst other things, manages the lateral navigation of modern aircraft. The current position is updated via GPS data from the GPS system and all available VOR and DME stations. Additional navigational information is provided by the compass system and ILS receivers. Together with the navigational database that contains data on magnetic variation, airways and waypoints, approaches for all relevant airports and radio navigation aids, it is possible by means of data fusion to calculate a very good estimate of the current navigational situation and prevent the runaway of the IRS itself through a feedback. It is even possible to deduce the current wind by combining the data with the true airspeed vector that is determined by the air data computer. The keypad and display that is normally associated with the FMS gives the pilot the ability to enter a flight plan that contains the departure, routing and intended approach. In flight, the FMS will present the route and other relevant information like the distance to the next waypoint and currently close by airports on the navigational display. You can also see the aforementioned wind vector in the corner. Finally, let's take a look at how aviation charts look like and how they are used. There are two kinds of flying. The first kind is called VFR, Visual Flight Rules. VFR means that you navigate primarily by looking outside, using visually identifiable references like rivers, bridges and highways. Nevertheless, the VFR charts contain, amongst information about such visual fixes, also information about radio navigation aids like NDBs and VORs that the pilot can use as additional reference. This is a VFR chart of the lower airspace around the city of Kassel. As you see, the emphasis of this map lies on the depiction of visible references, obviously. Good examples are these windmills in the west. The numbers depict the obstacle altitude above the sea level. These boxes show different airspaces and their horizontal and vertical extent. In different airspace classes, different rules of the air apply and have to be followed by all air traffic participants sharing it. Let's take a look at the VOR DME station depicted northwest of the city of Kassel. The rows, as you have already seen in our example, can be used for drawing lines based on received radials when airborne to estimate your current position. This is the name of the station, Warburg. The frequency of it is right below the name, 113.70 MHz. If you tune the station into the receiver, you should be able to hear the identification Morse code, which is WRB. To make it convenient for pilots who have not mastered Morse code, the beeps are depicted visually also. This way, the pilot can check that he is receiving the intended VOR station. Since VFR flights are only possible at good weather conditions, most professional or commercial flights are performed in IFR, Instrument Flight Rules. This way, pilots can navigate by instruments only, and therefore have to rely heavily on the navigation systems we have been talking about. To give you an idea how IFR flights are conducted, we will look at the approach chart for Chicago Midway International Airport for ILS runway 31 center. This may look confusing, but the good news is that we do not need all the information simultaneously. Let's assume that we are flying in from the south and are cleared for this approach. The first thing we have to do now is to prepare the navigational equipment. We know that we will eventually use the ILS. Therefore, one nav receiver has to be set on its frequency. We can read this frequency here, 109.9. Now we have to look for our initial approach fix that has to be overflown first in the beginning of the approach. Here it is. It's a VOR station called Chicago Heights, frequency 114.2. So we set our second nav receiver to this station. As we overfly the station, we should be at an altitude of at least 5,000 feet, or whatever the air traffic controller told us to be at. After we crossed Chicago Heights, we maintain 5,000 and follow the 011 radial outbound from the station. Now we are heading straight into the direction of the ILS signal, which is symbolized by this arrow. The next important point that we cross is the point where we intercept the ILS signal that will finally guide us to the runway. The point is called Hills and is, as we can see here, defined by the Chicago Heights radial 011 that we are currently on, the horizontal ILS signal from the airport, and the DME distance 14.1 miles. Down here you can see the vertical profile of our approach. We shall cross Hills at 5,000 feet and turn to the new heading of 315, following the ILS, and start descending. The next waypoint is Gleam and may not be crossed below 4,000 feet. After that, it's Runs with 2,500 feet above sea level and 6.7 DME. Hobel is the so-called final approach point, where we intercepted vertical guidance of the ILS at 4.2 DME at an altitude of 1,700 feet. Now the ILS will guide us horizontally and vertically to the runway. There is, of course, more vital information on this plate that has to be considered while flying this approach, but this would most definitely not fit into the scope of this presentation. You have seen the basic idea of the workflow of an IFR approach under normal operational conditions. You have seen an overview of selected items from the grand field of air navigation and instrumentation, from a simple compass to a highly complex inertial navigational system. You have also been presented the ways these tools are used in small and large aeroplanes. This presentation is in no way complete. There are other navigational techniques in use like Omega, GPS and stellar navigation, but you should now have an idea of what is out there. Thank you for watching, and as it is said amongst aeronauts, always happy landings.